Hello, my name is Alan, and today I will be talking about a new approach to conditional independence testing for Markov blanket feature selection. This was joint work with AmirEmad, Ghassami, Max Raginsky, Negar, Kiyavash, and Elyse Rosenbaum. Suppose we have a Bayesian network with a target variable y and feature variables x1 through xm, which are used to predict y. We call a feature subset x sub Sm a Markov blanket of y if it is a minimal subset of features such that it renders y conditionally independent of any other subset of features. In this sense, the Markov blanket is theoretically optimal. The Markov blanket of y consists of its parents, children, and co-parents, and is highlighted in blue for this example. In practice, the Markov blanket is found by performing a series of conditional independence tests, for example, in the spirit of the PC algorithm for structure learning. First, let's review some of the popular CI test approaches for continuous value data. In general, we classify CI tests as either non-parametric or model-based. Non-parametric methods estimate a test statistic that quantifies the level of dependence. These have been the method of choice for structure learning because they are simple and often work well in practice, but they tend to scale poorly with dimension due to the fact that they rely on kernel or KNN-based local density estimates. On the other hand, model-based methods use, for example, neural nets to model high-dimensional densities. In many cases, this allows them to overcome difficulties with high dimension. However, the challenge of using a model-based method is the computational complexity, since training a separate neural net for each CI test required is generally infeasible. We proposed a two-step model-augmented approach to CI testing for this problem. We first learn a low-dimensional mapping for each feature, and then perform CI testing using the KNN conditional mutual information estimator, using samples of the mapped features instead of those of the original features. If y and the mapped features are both low-dimensional, this approach allows us to perform the necessary CI tests using the KNN method without having to deal with high-dimensional variables. We next propose an efficient method for learning these feature mappings such that they preserve the CI relationships between the variables correctly, and the KNN estimator works well given the mapped feature samples. First, we're going to use f of x sub s to denote the set of mapped features corresponding to feature subset x sub s. Suppose that we have two distributions q theta I and q theta is with learnable parameters. We can minimize an upper bound on the mapping-induced CMI estimation error by maximizing the data likelihood of the learnable distributions over the parameters of the distributions and the feature mappings. However, this optimization objective applies only to a single pair of I and feature subset S. In order to learn a single set of mappings F1 through Fm that can be used for all of the CI tests, we need to maximize the likelihoods over all combinations of I and S. In order to do this, we consider a weighted objective over all possible feature subsets, each of which is encoded using a binary vector W, where the ith entry is 1 if the feature is present and 0 otherwise. We use f sub W of V to denote a masked set of mapped features, where the mapped feature is either present or set to 0 based on W. This allows us to optimize over a single parametric distribution that takes W as an additional input. In order to optimize this objective in practice, we treat it as an expected value over a random variable W. During each training iteration, we set a random feature subset to 0, somewhat in the spirit of dropout regularization. This is done by sampling W from a distribution. This allows us to learn feature mappings that preserve CI information across many different conditioning sets. The second goal is to ensure that the subsequent KNN mutual information and conditional mutual information estimator works well given samples of the map features. To illustrate, consider the bullseye example shown on the slide. X is uniformly distributed on two concentric rings around the origin, and Y is the magnitude of X plus some noise. In our proposed approach, we first learn a mapping of X and then use the KNN estimator to estimate the mutual information. One optimal choice of F would be to take the magnitude of X. However, in practice, we may end up learning different mappings for example, these two-dimensional mappings. As it turns out, it's the one on the left that leads to better KNN performance. This is because the KNN method relies on local density estimates and assumes that the neighbors of each data point have roughly uniform density. Therefore, when we are learning the feature mappings, we want values of X that contain similar information about Y to be mapped close together, and vice versa. We use this idea to define what we call the information efficiency property, and we introduce a regularization term that enforces this. Here, X prime is an identically distributed copy of X, and dj is the Jeffreys divergence. With this regularization term, we learn the illustrated feature mapping. As can be seen, the samples that have roughly the same distance from the origin are mapped close together as desired. We now compare the performance of several MI estimators using this bullseye example. The estimated MI is plotted against noise level on the left and sample size on the right. As we can see, the mapping approach outperforms the non-parametric nominal KNN method as well as the kernel-based Gini estimator. Adding the proposed regularization term further improves the performance, and the full proposed method performs comparably with the model-based Mayan estimator, as expected. Next, we compare the performance of several CI tests involving this Bayesian network, where the variables are distributed based on a 3D version of the previous bullseye example. Performance is plotted as a receiver operating curve of correctly identified CI relations out of a set. The proposed method showed the strongest performance, followed by the model-based CCIT, and finally the two non-parametric approaches. Finally, we apply our method to a feature selection problem involving real data. The problem here is to predict hard drive failures using diagnostic time series features. The plot compares the performance of three predictors using a receiver operating curve. The three predictors are trained using all of the data, features selected using the proposed approach, and a lasso type feature selection approach that we call L1. As can be seen, we identify a smaller subset of features using the proposed method as opposed to the competing lasso method, and we don't sacrifice predictive performance. In summary, we propose a CI testing approach for a Markov blanket feature selection when the features are high-dimensional that combines the computational tractability of non-parametric CI tests such as the KNN method along with the representational power of model-based methods. To this end, we propose a method that efficiently learns low-dimensional feature mappings which are used for the downstream non-parametric CI tests. We also propose an approach for improving the performance of KNN when given the mapped feature samples. We hope that this work will be useful for other problems where CI testing is a bottleneck due to dimension. Thank you.